The other approach that we have seen that may be used in representing signed binary numbers is called the complement system, or the 1's complement. And in general, if you have a base R number system and you want to find its R minus 1 complement, all you need to do is to subtract each digit from R minus 1. That is quite straightforward. For instance, you have a base 10. Therefore, our R base 10 is the one that we call decimal number system. And therefore, if you are asked to come up with a 9 complement, which you indicate as 9's, because we are saying R is 10 minus 1 becomes 9's complement, we are saying that you need to subtract each digit from R minus 1, which is 9. This is equivalent to 9. Therefore, for instance, if you are given, say, 127, which is a decimal number, you want to represent it using 9's complement. I'm not sure whether you have had such a scheme, but theoretically it's there. It can be called 9's complement scheme. Then you need to take, or you need to subtract each of these digits from 9. So you make your mean word 999 and you minus. Therefore, this would be 278. So if you wanted to represent 127 using 9's complement, it is going to be represented by 872. This may appear like quite a new concept, but that is what we are going. That is the same concept we are going to use when you're talking about binary number system. So in the decimal number system, the R minus 1 complement is referred to as the 9's complement, and in the binary system, it's referred to as the 1's complement, because we are saying in binary the base is 2. Therefore, when we say R is 2, we're talking about R minus 1's complement. So the R minus 1's complement is 2 minus 1 becomes 1. Therefore, we call it 1's complement. So we would follow the same idea. And in similar manner, because our R is 2, or the one that we call as 10 in the binary, in the decimal case, so in our case, R is 2, you'd say 2 minus 1 is the number you're going to subtract all the numbers you want to represent from 2 minus 1, which is equals to 1. So for instance, assume we will have a 5. 5 in binary numbers is represented by 101, and we therefore say that if this is the number you want to convert to 1's complement, you need to subtract each digit from 111, because this one is equivalent to a 9. Therefore, you subtract, you find this is 0, this is 1, this is 0. Therefore, 5 in 1's complement would be represented by 010. So the 1's complement provides an alternative method of representing binary numbers. And if we do a very quick example, we want to obtain the 1's complement of 10111. As I have said, you need to take all 1's equivalent to the digits that you have, which are 6 in this case, and then you minus. You can even write them here up here. So you just need to subtract. I'm just following this rule that we have read here. Therefore, you'd say 1 minus 0 is 1. 1 minus 1 is 0. 1 minus 1 is 0. 0, 1, 0. This number is represented by this as its 1's complement, and you'll find their use when performing binary arithmetic. So it can be observed that the 1's complement may be obtained by interchanging zeros and ones and ones and zeros. So in this example that we have just done, or I can just write it here, we converted 5 in binary to its 1's complement, and we found that we were minusing from 111, and we found the answer to be 010. This is equivalent to interchanging each digit with it. If it is a 1, becomes 0, and 1, 0 becomes 1. And therefore, we are saying that the simplest way of performing 1's complement is if you are given 10111, every 1 becomes a 0, and every 0 becomes a 1. So this would become 01000. So that is another very important idea that we observe regarding 1's complement. In the 1's complement, positive and negative numbers are represented as follows. So we normally use the 1's complement to represent negative numbers, and therefore we say that the positive numbers do not change at the 1's complement scheme, but the only thing we make sure we add is that the most significant bit must be a 0. But the negative numbers are represented by its ones complement. So for instance, if you have a 5, 5 will not be changed. We'll only use its ones complement when we want to represent minus 5. That is when we will have this ones complement, and as we have seen here, we say that you interchange every bit. So if it is a 0 becomes a 1 and a 1 becomes a 0. Therefore, we are saying this number will represent negative 5 and this number will represent a 5. So this means that the negative number has the most significant bit always as a 1, and that is important because you always want to have a scheme that you are able to identify when you are representing a positive 1 and a positive 0. Therefore, in that example that we have just given, we cannot just represent 5 as such. So if we had a 5 which is 101, we would always add a 0 to them as its most significant bit, so that if you are to represent a negative 5, it will reverse to become 1 0 1 1 0. Therefore, we know that whenever we find a positive or a 1 as the most significant bit, that means it's a negative number. So as I also mentioned, there are times you'd specify a limit on the number of bits that you are going to use to represent a number. And in this case, we are asked to use 8-bit scheme using the ones complement representation to represent positive 37 and negative 37. So the same way we did the conversions of decimal numbers to binary numbers, you need to do, you can use whichever method, be it repeated division by 2 or the positional weights, and I prefer the positional weights because I am able to know that the multiple of 2 that is less than 37 is 32, which is represented by 2 to the power 5. So I would start with 2 to the power 5, 2 to the power 4, 2 to the power 0, and I know if I take 37 minus 32, I will be left with 5, so this will become a 1, and I will find this being a 0. So for me to get a 5, I will take a 4. So I will take a 1 there, and I will take a 1 there. This will become a 0. So this is our number 37, positive number 37 in binary numbers. So if we were to use 8-bit scheme, we would count these to be 1, 2, these are 6, and therefore we would represent that positive 37 as equals to 0, 0. We add 2 preceding zeros before the magnitude that is representing 37, which is now 1, 0, 0, 1, 0, 1. So this is now our positive 37. So if you are to represent this same number using the ones complement scheme, all we need to do is to reverse this one and say this now becomes 1, 1, 0, 1, 1, 0, 1, 0. So now negative 37 is represented by that number using ones complement method. So in summary, we see that 37 is represented by 100, 101, and we add 2 zeros that precede these 6 digits. We have 0 zeros preceding 100, 101, and then for the ones complement, we just reverse all those zeros to become ones and ones to become zeros, and therefore you find that minus 37 is represented by 11011 010. So that is the use and application of ones complement in representing negative numbers. In conclusion, we see that also the ones complement has a dual representation of a 0, because if you are given a positive 0 using 8-bit representation, it would have a 0 as the most significant bit. But if you are told to represent a negative 0, then you would reverse all the zeros and you actually realize that this 0 or this negative 0 is represented by all these ones, because just following the rules, we have said for us to obtain the ones complement, you need to reverse zeros to become ones, and therefore this becomes a dual representation of 0, which again is unpreferable or undesirable for arithmetic operations to be done by computing devices. Therefore, it is not widely used because of this reason in most computer systems.